So imagine for a second that you were standing in a pitch black room, completely dark.
That's a stressful start.
Right. And, for a fact, that someone hiding in the dark is winding up to throw a baseball right at you.
Yeah, no thank you.
But here's the thing. You have absolutely zero idea when they are going to throw it. You don't know what direction it's coming from. You don't know how fast it's moving. It's just total uncertainty.
You're completely blind to the variables.
Exactly. So how does your brain physically prepare for an event when it has zero information about what to actually expect?
It's a huge question.
It really is. And welcome to this deep dive, by the way. If you have ever wondered how the human mind deals with the absolute terrifying unknown, we actually have a fascinating answer today.
We do, and it comes from a really dense, incredibly intricate 2026 paper.
Yeah, published in Nature Neuroscience. It's by researchers Daria Frank, Brian A. Strange, Carl J. Friston, and their whole team.
And our mission today is to completely unpack how your brain physically, at a cellular level, predicts the future.
Because the setup for this research is just, it's just as compelling as the findings themselves, honestly.
It really is. I mean, usually when we talk about brain imaging on this show, we are talking about fMRI scans, right, which track blood flow.
Right, but blood flow is sluggish. It changes over seconds.
Exactly. The brain operates in milliseconds, so fMRI is too slow. Or we use surface EEG, which is essentially, putting those little sticker electrodes all over the scalp.
But the problem there is that the electrical signal has to travel through fluid and bone and skin.
So it gets incredibly muffled by the time it reaches the sensor. But this paper bypasses all of that entirely. They used intracranial local field potential recordings.
Which means they literally have wires placed deep inside the brain tissue of living, awake human beings.
17 patients, to be exact.
That is just wild to think about.
It is. These are individuals with severe epilepsy who had these depth electrodes surgically implanted to locate the origin of their seizures for their clinical treatment.
So the researchers aren't just drilling into heads for fun. The wires are already there.
Right. And with the patient's consent, the researchers can sort of piggyback on this medical setup to record neural activity at the millimeter level in real time.
And we should emphasize, in human neuroscience, this is the absolute gold standard of evidence, like grade A.
Without a doubt. It allows us to observe the incredibly fast, raw electrical dynamics of the brain that would otherwise be completely invisible to us.
Okay, so we have this unparalleled access to the brain's hardware. But before we look at the specific regions that are, lighting up on these wires, we need to talk about the software.
We have to fundamentally shift how we think about what the brain is actually doing from second to second.
Right, because most of us grow up thinking of the brain like a video camera. Like your eyes take in light, your ears take in sound, the camera records it, and then your brain reacts to it.
But that passive camera model is incredibly outdated in neuroscience. This paper operates under the predictive coding framework, which is a concept heavily championed by Carl Friston under the free energy principle.
And this is where it gets really cool. Your brain is locked inside this dark, silent, bony vault, the skull, has no direct access to the outside world.
None at all. It only receives these ambiguous electrical pulses.
So rather than waiting for information to arrive and trying to, decode it from scratch every time, the brain acts as a generative model.
Right. It is constantly projecting predictions outward. It's guessing what is about to happen and using the incoming sensory data merely to check its work.
And it does this because guessing wrong is physically expensive. If the brain is shocked by something unexpected, it takes a massive amount of metabolic energy to fire all the neurons needed to process that surprise and update its model.
And evolution hates wasting energy.
Exactly. It wants to minimize those prediction errors.
So to manage this efficiently, the brain relies on a mathematical distinction between two concepts that we often just conflate in everyday language.
Entropy and surprise.
Right. In information theory, entropy is a measure of unpredictability before an event occurs. It is the expected information gain, or basically how much uncertainty exists in the environment right now.
Whereas surprise, which is technically termed self-information in the math, is how unexpected the event is after it has actually occurred.
Exactly.
So to use an analogy, entropy is like staring up at dark, swirling storm clouds. You know something wild is going to happen, you just don't know exactly what or when.
The environment is highly uncertain.
Right. Surprise, on the other hand, is the moment a bolt of lightning actually strikes the tree right next to you. It's the post-event shock.
That's a great way to put it.
So if you're listening and you need a way to lock that in, just remember EPS. Entropy prepares, surprise strikes.
EPS. I like that. And that EPS framing is very useful for understanding the researchers' experimental design here.
Because they needed to test how the human brain handles both the storm clouds and the lightning strike.
Right. Without relying on memory, exactly. So they had these 17 patients sit in front of a screen and perform a simple visual-motor task.
Sequences of colored shapes would appear, and the patients just had to press a button corresponding to the shape they saw.
Right, so there was no complex pattern to memorize.
Huh?
But the researchers simply altered a probability of certain shapes appearing.
Sneaky.
Very. By subtly shifting the odds in different blocks of the experiment, they could mathematically dial the entropy and the surprise up or down.
They could basically change how chaotic the storm clouds were and how often the lightning struck.
Exactly. And they knew the patients' brains were actually tracking these invisible probabilities because they looked at their reaction times.
Right, because of Hicks' law, right.
Yep, the behavioral data aligned perfectly with Hicks' law, which is this well-established psychological principle stating that as the uncertainty of a choice increases, the time it takes to make a decision increases logarithmically.
So as the mathematical bits of entropy and surprise increased on the screen, the patient's reaction times reliably slowed down.
The brain was taking longer to process the visual information because its internal predictions were less certain.
Okay, so to quickly recap our first block here. The brain acts as a prediction engine, right? Not a camera.
Right.
And entropy is that pre-event unpredictability, while surprise is the post-event shock.
Spot on.
So I want you, the listener, to think about your own day for a second. When are you operating in a state of high entropy versus high surprise? It's kind of wild to realize your brain is doing this math constantly.
It really is.
Okay, so the brain is acting as this constant prediction engine, weighing the odds of the unknown. But where is the physical engine doing the math?
Well, you'd think it would be the prefrontal cortex, right?
Yeah, that's exactly my first thought, the logical planning part of the brain. But this paper points somewhere entirely different.
It points deep into the temporal lobe to the hippocampus.
Which is universally known as the memory center. Like, it's where we consolidate facts and navigate physical spaces.
Usually, yes. But in this context, the hippocampus acts as a sophisticated probability engine. To see this engine at work, the researchers analyzed the recordings from those depth electrodes we talked about, and they isolated something called sharp wave ripples.
Sharp wave ripples.
Yeah, or SWRs. These ripples are massive, synchronized bursts of electricity, and they oscillate incredibly fast between 140 and 200 hertz.
That is fast.
They're generated by a highly complex interaction between excitatory neurons, which push signals forward, and inhibitory neurons, which act as the brakes.
Now, in the past, I've read about these ripples occurring when, like, a mouse is navigating a maze. The mouse pauses and its hippocampus fires off these ripples to quickly replay the route it just took, or pre-play a route it might take next.
That's the classic understanding, yes.
But as you mentioned, this shape task didn't require any memory or navigation. So why on earth is the hippocampus firing off these massive electrical bursts just for shapes on a screen?
Well, out of 2,728 ripples detected across all the patients, the researchers noticed a dramatic clustering.
Like they were happening at very specific times.
Exactly. There was a massive spike in ripple generation, specifically between 800 and 400 milliseconds before the shape even appeared on the screen.
Wait, before?
Yes, prestimulus. And this spike only occurred when the environment's entropy was at its highest, around 1.7 to 1.9 bits of uncertainty.
So when the storm clouds were the darkest.
Exactly. Furthermore, as the entropy mathematically increased, the actual physical duration of these electrical ripples lengthened.
Okay, hang on though. Let me play devil's advocate. If I am sitting there and the shapes on the screen are completely random and bizarre, my brain is going to be highly stimulated.
Sure.
Couldn't these ripples just be the hippocampus reacting to the fact that it keeps seeing weird, unpredictable shapes? Like maybe it's just reacting to the shock rather than predicting the uncertainty?
That is a very important distinction, and it's something the researchers actually controlled for beautifully.
Oh, they did?
Yeah, using a separate data set from an oddball paradigm.
Okay, how does that work?
In this control task, patients read standard lists of words, but occasionally a word would flash on the screen in a completely bizarre, unexpected font.
Ah, okay. So that strange font creates a high level of surprise. It is a pure prediction error.
Exactly. It's the lightning striking when there were no storm clouds to warn you.
Right.
And when they analyzed the hippocampal activity during those oddball moments, there was no increase in ripples whatsoever.
Really? None.
None. In fact, as surprise increased, ripple counts generally trended downward.
Oh, wow.
This definitively proved that ripples are not a reaction to shock. They are a preparatory mechanism.
So the hippocampus uses these bursts to broadcast the expected uncertainty of the environment. It's essentially warning the rest of the brain, get ready, something highly unpredictable and informative is about to happen.
Precisely.
Okay, time for our second quick recap. The hippocampus isn't just for memories, it literally predicts the future.
Yes.
And these ripples are fast electrical bursts acting as what-if simulators, and they spike for unpredictable events, not after surprising ones.
That's the core of it, yeah.
So, to our listeners, if ripples are your brain simulating options, how intensely do you think your hippocampus is rippling before you walk into a totally unpredictable job interview?
Oh, I bet it's just humming.
Right, just a constant buzz. Okay, so the hippocampus knows the environment is unpredictable, but the hippocampus isn't the part of the brain that actually sees the shapes.
No, it's not.
That's the visual cortex at the back of the head. So how does a ripple deep inside the temporal lobe actually change what your eyes process?
To map that communication, we have to look at a different electrical frequency entirely. The gamma band.
Okay, what's the frequency for gamma?
It operates between roughly 57 and 97 hertz.
Got it.
In predictive coding, gamma waves are typically the messengers for bottom-up prediction errors. They basically carry the news of what the eyes are actually seeing up the chain of command.
And the researchers tracked this gamma activity along the cortical hierarchy, right?
Yes, starting at the occipital cortex, which handles raw, basic visual data like lines and light, and moving up to the fusiform gyrus, which handles complex, higher-level processing like actual object recognition.
Okay, so what actually happens to those visual areas when the hippocampus fires its warning ripple?
There is a very specific ripple-triggered cortical response.
Okay.
When high entropy triggers that prestimulus ripple in the hippocampus, the baseline gamma power in the occipital cortex is actively suppressed right before the image appears.
Actively suppressed. Okay, I have a visual for this. It sounds like a theater director realizing the next scene in the play is entirely unscripted.
Okay, I follow.
Like anything could happen. So the director, the hippocampus, turns to a noisy audience and aggressively shushes them.
I like that.
It quiets down the baseline chatter in the occipital cortex that when the actors finally speak, and the visual data actually arrives, the cues can be heard with absolute pinpoint clarity.
The director's hush. That is a very apt way to describe it.
It helps it stick in the memory.
It does. The hippocampus is actively reaching out and modulating the cortex, temporarily altering its physical state, so the incoming sensory data isn't drowned out by background neural noise.
Let's lock this down with another quick recap. Gamma waves signal prediction errors in the visual cortex, and hippocampal ripples actively modulate that cortex, meaning those pre-stimulus ripples suppress baseline occipital noise. They hush the audience to prep for incoming data.
Exactly.
So think about your own experiences for a second. Have you ever felt that mental hush right before something chaotic happens where your senses suddenly just sharpen? That is your hippocampus at work.
It's literally changing the physical state of a brain.
Which makes sense conceptually, but how does that hush physically alter the tissue? Like, what is happening at the cellular level that makes the cortex better at processing the surprise when the shape finally hits the screen?
Well, this is where the researchers utilized a really clever analytical tool called the FOOO method to measure the tissue's physical state.
Wait, FOOF?
Right.
Like the sound?
Yeah, it stands for fitting oscillations and 1/F.
Okay, you've completely lost me there. 1/F. What does that actually look like in the brain?
Right, sorry. Think of it as a way to separate the actual rhythmic brain waves from the background static.
Okay.
If you plot brain activity on a graph with low frequencies on the left and high frequencies on the right, you get a line that slopes downward.
I'm picturing a ski slope.
Good. The steepness of that slope, which is called the aperiodic exponent, tells us the global state of the tissue. Specifically, it measures the balance between excitation and inhibition.
Meaning basically how easily the neurons are triggered to fire versus how strongly they are being held back.
Precisely. Without a preceding ripple, the fusiform cortex naturally sits in a highly excitatory state.
So the ski slope on our graph is flatter.
Right, meaning there's a lot of high-frequency noise, the neurons are trigger-happy, but when a prestimulus ripple does occur, it dramatically alters that environment.
How so?
The slope gets much steeper. This indicates that the fusiform cortex has shifted into a beautifully balanced, highly inhibitory state.
Okay, I think I have another analogy for this one.
Let's hear it.
Imagine the cortex as a tennis racket. If the strings are incredibly loose, which is your highly excitatory state, there is no control. Any incoming ball just flubs off the racket unpredictably.
Right.
But the inhibition, that steep slope triggered by the ripple, is like tightening those strings to the absolute perfect tension. The racket is primed. When the ball finally arrives, those tight strings allow you to smash it back with incredible precision.
That is a perfect analogy. In the engineering world and in Friston's predictive coding models, that tightening of the strings is called the Kalman game.
The Kalman game?
Yes, it is how a system applies precision weighting to a prediction error. It mathematically determines how heavily the system should trust this new incoming piece of information.
Ah.
Because the fusiform cortex is perfectly prepped, sitting there with tightened strings, thanks to the ripple, the post-stimulus results are striking.
What happens when the shape actually appears?
When the surprising shape finally hits the screen, the fusiform gamma response is significantly faster. It launches between 250 and 550 milliseconds.
Wow.
And it's far more powerful than when no ripple prepared the area.
The tight strings let the brain return the volley faster and harder.
Exactly.
But does the visual cortex just process the image and leave it at that? Or does it report back to the director? Like, does it tell the hippocampus what happened?
It reports back, and we know this because the researchers measured something called Granger causality.
Okay, break that down for me. I know Nobel laureate Clive Granger developed it for economics, but how does it work in neuroscience?
In simple terms, Granger causality is a statistical test for directed information flow. It asks, who is driving the conversation right now?
Okay.
If the past activity of region A helps predict the future activity of region B better than region B's own past does, we can safely infer that region A is sending information to region B.
And when the researchers applied this math to the patient data, they found a distinct sequence.
They did.
So they can see the actual direction the signals are traveling in real time.
Yes. And they found that after the surprise is processed by the visual cortex, the Granger causality flips.
The flow of information reverses.
Exactly. The fusiform cortex begins sending gamma signals back up to the hippocampus.
It closes the loop.
Yes.
The hippocampus says, get ready, things are uncertain. The visual cortex tightens its strings, processes the weird shape flawlessly, and then fires a message back saying, here is exactly what the strange shape was. Update your generative model.
It is a stunningly elegant system of neuronal message passing.
It really is.
It completely validates the view of the brain, not as a passive receiver of reality, but as a proactive engine. The hippocampus isn't just a hard drive recording what happens to us.
Right.
It is broadcasting the predicted precision of upcoming events, physically tuning the excitatory and inhibitory balance of our sensory areas to ensure that when we encounter the unknown, we learn from it efficiently.
Okay, final recap of the mechanics here. Ripples create an inhibitory tight string state in the fusiform. This allows the brain to process surprise faster and more precisely. And finally, the visual cortex then updates the hippocampus on what actually happened.
That's the entire mechanism, in a nutshell.
So, listener, how efficiently do you think your mental racket is strung when you're, say, sleep-deprived versus fully awake? I'd imagine lack of sleep totally ruins this delicate EI balance.
Oh, absolutely.
It's just an incredible piece of machinery. We've talked about milliseconds and mathematical probabilities today, but I want to zoom all the way out for a second to close this out.
Okay, thanks, do.
If our brains, specifically our hippocampi, evolved over millions of years to rely on these ripples to prepare for the wild, chaotic unknown of the natural world, it raises a really provocative question about the way we live today.
Where are you going with this?
Well, think about your daily life. The routes you drive are optimized by GPS so you never get lost. The shows you stream are perfectly fed to you by recommendation engines. The information on your social media feed is algorithmically curated to align perfectly with your existing worldview, explicitly designed to eliminate prediction errors so you never feel uncomfortable.
We have engineered a world of frictionless predictability.
Exactly. Are we literally starving our brains of entropy?
That is a fascinating thought.
If the hippocampus needs the chaos of the storm clouds to trigger these vital preparatory ripples, what happens when we never have to face the unknown anymore?
Right, are those neural pathways going dormant?
Are we losing our ability to string the racket? It is something to seriously mull over the next time you find yourself standing in the dark waiting to see what gets thrown at you.
Couldn't have said it better.
Thank you so much for joining us on this deep dive into these 2026 Nature neuroscience findings. Stay curious, and we'll catch you next time.